Welcome to the second day of Summer General Physics. In this third video, we'll be looking at an example where we will need to add 3 displacement vectors. So in this example, let's say we have a boat that travels 100 meters due south, then it turns and travels 200 meters in a direction that is 20 degrees south of east, and then it travels for 50 meters in a direction that is 10 degrees north of east. What is the resultant displacement of the boat? That is, how far is it from its starting point in a straight line? So to solve this problem, the first thing we'll want to do is to draw a picture showing these 3 displacement vectors. So let's do that. So before we start drawing a picture even, we need to figure out our coordinate system and what our coordinate directions will be. So we'll probably choose a Cartesian coordinate system for this problem and have the directions correspond to north, south, east, and west. So if we choose those as our coordinate directions, let's draw the motion of the boat. So first of all, the boat travels 100 meters in a direction that is due south. So let's draw that. So first the boat goes due south, and it does that for a distance of 100 meters. Then the boat turns and travels 200 meters in a direction that's 20 degrees south of east. So what does south of east mean? Well, if you think about giving someone ordinary directions, you might say that the church is 2 miles east of the grocery store. What would that mean? It means you start at the grocery store and travel that distance in the east direction. So with angles, it's pretty much the same thing. South of east means we start in the east direction and then go 20 degrees south of that. So if I'm to draw that, I'll need to add my vectors tip to tail. So let's draw a little bit of a coordinate system at the end of my first vector. So this would be the east direction. And so 20 degrees south of east means I would start with my vector pointing in the east direction and then drag the tip of that vector 20 degrees in the south direction, south of east. So that means the second vector is going to look something like this. It's 20 degrees south of east, and it has a length or a magnitude of 200 meters. Then finally, the boat undergoes a displacement 50 meters, 10 degrees north of east. So once again, if I draw a bit of a coordinate system here at the tip of my second vector where I'll add the third, I need to add this third vector so that it's pointing in a direction that is 10 degrees north of east. So I start out in the east direction and drag the tip of that vector 10 degrees in the north direction. So that means the final vector will look something like this. It will have a length of 50 meters and be at an angle that is 10 degrees north of east. Okay, so those are my 3 vectors. And when I add those 3 vectors together, I will get a resultant vector that goes from the tail of the first to the tip of the last, something like that. This will be my resultant vector. And so I need to figure out the length of that resultant vector and also what angle is it pointing. So the next step, now that I've drawn a picture of the overall journey, is to take each one of those vectors individually and break them into x and y components. And as I do that, I like to fill out a table. So in my table, I'll have the name of the vector, and then break it up into an x component and a y component. So I need to go back and label these vectors. I'll call the first vector vector A, the second vector B, and the third vector vector C. So I'm adding together A, B, and C, and when I sum those together, I will get my resultant vector. All right, so next I need to break these vectors into x and y components. So let's look at each vector individually, and this is something you'll always want to do. You'll always want to, when you're breaking the vectors into x and y components, draw a picture of each vector individually with its own coordinate system. So first off, let's look at vector A. So if I draw a coordinate system, and then I draw vector A, there's vector A. It has a length of 100 meters. We can see that vector A points totally in the negative y direction. There's no component in the x direction at all. So this one's easy to break into x and y components. The x component is going to be 0. I can put that in my table. And the y component would be 100 meters long, and it's in the negative direction. So I've broken that first vector into its x and y components. So next let's take a look at the second vector, which is vector B. So vector B isn't going to be quite as simple as vector A because it has a component in both the x and the y directions. So it makes an angle of 20 degrees with the positive x-axis, and it has a length of 200 meters. So this is my vector B. So I need to break this vector up into x and y components. So let's drop a line between the x-axis and the tip of my vector. If I do that, and if I make it 90 degrees with respect to the x-axis, you can see that this side of the triangle, which is a right triangle, is my x component, and this side is the y component. So then if I consider my trigonometric functions, if I first take the sine of that 20-degree angle, sine of 20 degrees is going to be the opposite side, which is the length of the y component, divided by the hypotenuse, which is 200 meters. So that means my y component is going to be equal to 200 meters times the sine of 20 degrees. And if I plug that into a calculator, I should get a value that is about 68.4. Okay, so then I can put that into my table. The y component has a length of 68.4 meters, but then I'll notice that it's in the negative y direction. The B vector is pointing below the x-axis. It's pointing in the negative y direction, so I'd better put a minus sign here. Okay, so then what about the cosine of 20 degrees? So the cosine of 20 degrees is going to be equal to the adjacent side to 20 degrees, so that would be the x component over the hypotenuse of 200 meters. And so that means my x component would be 200 meters times the cosine of 20 degrees, or 187.9 meters. So then I can add that to my table as well. 187.9. And the x component of this vector, well, this vector is pointing in the positive x direction. So since it's pointing in the positive x direction, the number I write down in my table should be also positive. All right, so I've broken up A and B into x and y components, and the third vector is, of course, vector C. So if I draw a picture of vector C all by itself, here is vector C. So vector C has a magnitude of 50 meters, and it's in a direction that's 10 degrees north of east, or 10 degrees above the positive y-axis, or x-axis. So if I once again drop a line to the positive x-axis, I can see that this side is the x component of this vector, and this side is the y. And so once again, I can break the vector up into x and y components. So let's see, if I take the sine of this 10-degree angle, then the sine of the 10-degree angle would be opposite over hypotenuse. And if I solve for y, that gives me y is 50 meters times the sine of 10 degrees. And if I look at that value, plug that into my calculator, I get 8.7 meters. So I would put that in my table, 8.7 meters. And that's in the positive y direction. And then if I consider the cosine of my 10-degree angle, the cosine of 10 degrees would be adjacent, which is the x component, divided by the hypotenuse of 50 meters. So then the x component would be 50 times the cosine of 10 degrees. And that has a value of 49.2 meters, which I'll write in my table. 49.2 meters. All right, so that's the x component, which is pointing in the positive x direction. So that would be a positive x component. So then the next step is to add together all of the x components to find the x component of my resultant vector. So that would be 237.1 meters. And likewise, I want to add together all of the y components, which will give me a negative 159.7. So now I have the sum of the x components and the sum of the y components, giving me the x and y components of my resultant vector. So now that I have the x and y components of my resultant vector, I can go ahead and find the length and the direction of that resultant vector. So I'll need to erase this so I have more room. Now, just as a reminder, what we found before was that my resultant vector's x and y components were, the x component was 237.1 meters, and we found that the resultant vector's y component was negative 159.7 meters. So let's draw that vector. Okay, so the x component is positive. So if I'm drawing my x component, it should point in the positive x direction, and it will have a length of 237.1 meters. The y component is negative, so it must point in the negative y direction, 159.7 meters long. So my resultant will look something like this. Here is my resultant vector, and it's going to have some magnitude or length, and it will also be at some angle with respect to the positive x-axis. So first, let's find the length of my resultant vector. So to find the length, I can use the Pythagorean Theorem, and the resultant will be equal to the square root of the x component, 237.1 meters squared, plus the length of the y component, 159.7 meters squared. I take the square root of that, and I get a value of 285.9 meters. So that's the length of my resultant vector. I know that the boat at the end of these three displacements will be a total distance of 285.9 meters from its starting point. I also want to find this angle that the resultant vector is pointing at, so I can find that angle using some trigonometry. Specifically, if I look at the tan of that angle, the tangent would be the opposite side, 159.7 meters, divided by the adjacent side of 237.1 meters. And so I would need to then take the inverse tan of whatever this ratio happened to be. And if I do that, I would find that the angle I get is equal to about 33.96 degrees. So let's round that to 34 degrees. So when I'm reporting this, I could report the angle in a couple of different ways. I could either say that my angle is negative 34 degrees, implying that it's below the positive x-axis, or I could say that the angle was 34 degrees south of east, because I could get this direction by starting in the east direction and then pulling the vector down 34 degrees towards the south direction. So that would be my answer. The magnitude of my net displacement vector is 285.9 meters in a direction that is 34 degrees south of east. Now, one thing that you may have noticed when I was breaking the vectors into components for this problem is that I seem to always use cosine for the x component and sine for the y component. And I want to warn you now that that's not always going to be the case. So for example, let's say I had a vector that was pointing in some direction, and I was given the angle, instead of with respect to the x-axis, I was given the angle with respect to the y-axis. Let's say it's 20 degrees as an example. So as you can see from this picture, if I were to draw a line like this and try to find the x and the y components, in this case, the x component is opposite the 20-degree angle. So I would use sine of 20 degrees as being equal to the x component divided by the hypotenuse, which would be the length of my vector. Let's call it L. So in this particular case, I would take the sine of 20, and I would use the sine to find the x component and the cosine to find the y component. So it's always best practice when you are given a problem where you have to break vectors into x and y components in order to add them. It's always the best idea to draw a picture where you can see clearly where the angle is, with what axis is it with respect to, and therefore what trig function you should use to find which component. Okay, so let's look at a couple of questions. In this first question, if vector b is added to vector a, the resultant vector, a plus b, has a magnitude a plus b when a and b are, and we have some options here. So what this question is asking is, when is it okay to add together the magnitudes of the two vectors? If I know the magnitude of a and the magnitude of b, when can I just add those magnitudes or lengths together to find the length of the vector sum? What orientation do a and b need with respect to each other? So pause the video here and give this a little bit of thought, then come back when you've decided on your answer. Okay, so now that you've had a chance to think about this question, we should try to decide, when is it okay to just add the lengths of two vectors together to find the length of the vector sum? So let's consider these cases. The first is when the two vectors are perpendicular to each other. So if we drew a picture of what that looked like, let's say this is vector A, and let's say this is vector B. if they're perpendicular to each other, if I add this length with this length, do I get the length of the vector sum? No, that really wouldn't work. If they're perpendicular to each other, you really can't add the two lengths of the vectors and expect that to be equal to the vector sum. What about when they're in the same direction? So that would look like, let's say this is vector A, and vector B points in the same direction. Then when I add those two vectors together, the resultant would look something like that. And in this case, it is okay to add the two lengths of the vectors together. So if A and B point in the same direction, we can take the length of each, sum it, and get the length of the vector sum. So actually, that is our answer. If we had the opposite directions, then that would be like, here's vector A, here's vector B, and the sum would go from the tip of the first to the tail of the last, so the resultant vector from adding A plus B would look like that. And in this case, you can see that the length of the resultant would actually be the difference between the lengths of the two vectors. So what we want is B. They have to be oriented in the same direction for it to be okay just to add the lengths. All right, how about this question? Let's say the magnitudes of two vectors A and B are 12 units and 8 units respectively. What would be the largest and smallest values for the magnitude of the resultant A plus B? So pause the video here, give this a bit of thought, and return when you have your answer. Okay, so now that you've thought about it, what did you choose for your response? If A and B are 12 units and 8 units, what's the biggest possible vector we could get by adding them? So the biggest possible vector we could get by adding them would be in the case where the two are pointing in the same direction, right? So let's say if this is A and this is B, if they're in the same direction, then we can add their lengths together, and 12 units and 8 units, if we add them together, we would actually get what? We'd get 20, which isn't really one of our answers. Oh, there it is. So 20. We would have a vector that's 20 units long as the resultant. What if the two vectors were arranged so that they were opposite to each other? So this was the 12 one, and this is the 8. Then the resultant would look something like this. And 12 minus 8 would be 4. So I guess we would want answer C. 20 and 4. That's the biggest, that's the smallest we could get. If we have any other orientation, say something like this, then the resultant would be somewhere in between. So that concludes the third video. In the next video, we'll be looking at displacement and velocity.